Hi, my name is Brandon Mazzara, and I'm in EECS 203 at the University of Michigan, and I'm going to be talking to you about the Monty Hall problem. So what is the Monty Hall problem? Imagine you're on a game show and you have to choose to open one of three doors. Behind one is a large prize, and behind the other two is nothing. After you select a door, the host opens a different losing door. Now he gives you the option of switching doors or keeping your original choice. Should you switch doors, or does it not matter? Alright, so imagine you have three doors, A, B, and C. Inside door B is the prize, and the other doors have nothing. So imagine you choose door A. In this case, since after you choose door A, the host will open a losing door, and the only losing door is C, if you switch, you will switch to door B and you will win. So if you choose door A, you'll win. Now imagine you choose door B. In this case, the host will open either A or C. If the host opens door A and you switch, you'll choose door C and you'll lose. If the host opens door C, you'll choose and you switch, you'll choose door A and also lose. So if you originally choose door B, the winning door, and you switch, then you'll lose. Now if you choose door C, the host will open door A, and if you switch, you'll choose door B. That will lead to a win. Now you may think that since there's two possibilities of you winning and two of you losing, then it doesn't really matter if you switch or don't switch. But these four choices don't actually have uniform probability. Since you have a 1/3 chance of choosing door A, B, or C, then there's a 1/3 chance that you'll choose door A and win, and a 1/3 chance that you'll choose door C and win. But since there's two sub-probabilities of door B, the host choosing to open door A or door C, then for each of these choices, there's a 1/2 probability. So the total probability of choosing the path that you choose door B and then switch to door C after the host opens door A is 1/3 times 1/2 equals 1/6 by the product rule, and the same for this case. So adding the two cases in which when you switch you'll win, so if you choose door A or door C, means that there's a total of 2/3 probability that if you switch you will win. And adding the two probabilities that if you switch then you'll lose, this means that there's a 2/3 probability that when you switch you'll win and a 1/3 probability that when you switch you'll lose. It doesn't even matter if the host only has 1/2 probability of choosing door A or C. Let's say that the host has a P probability of choosing to open door A if you originally choose door B, and then a 1 minus P probability that he'll open door C if you choose door B. Then summing these probabilities to get the probability that when you switch you'll lose, you get still only a 1/3 probability that when you switch you'll lose, meaning that there's still 2/3 probability that when you switch you'll win. Thus, you should always switch. We can also prove that switching will win 2/3 of the time by using this identity that P, the probability of event E, equals the probability of event E given F times the probability of F plus the probability of event E given not F times the probability of not F. Now let's define E to be that I2 has the prize, meaning that the box that you switch to has the prize, and F being I1 has the prize, I1 being the original box that you choose. Thus, PE given F is the probability that the box that you select after switching has the prize, given that the box that you originally choose has the prize, and this probability is going to be 0, because if the box that you already select has the prize, then the box that you switch to can't have the prize. The probability that I1 has the prize is just going to be 1/3. Now the probability that the box that you switch to has the prize, given that the box you originally select does not have the prize, is going to be 1, because whenever you select a box that does not have a prize originally and then switch, the box that you switch to is going to have the prize. And then the probability that the box that you originally select does not have the prize is going to be, that's the probability that the box you select is empty. So summing this, we get, which means that the probability that the box that you select after switching has the prize is 2/3, meaning that the probability that switching wins is 2/3. In general, given n doors and m different prizes in the doors, we'll show that even in the general case, it's always better to switch. So let's let E be the event, again, that the box that you switch to has the prize. Now given n boxes and m boxes that have prizes, the probability that the box that you select after switching has the prize, given that the box you selected originally has the prize. So let's say that you originally select this box, then the host opens this box. So since there are m-1 prizes left, and the total sample space is now n-2, this is that probability. Now the probability that the box that you originally select has the prize is just going to be m/n. Now the probability that the box that you select after switching has a prize, given that the box that you originally select is empty. So let's say that you originally pick this box, then the host opens this box. So now the total number of prizes left is still m, and the total sample space is n-2. And the probability that the box that you originally select is empty is going to be, since the total number of boxes that are empty is going to be the total number of boxes minus the number of boxes with prizes is n minus m, and the total sample space is n, then this is that number. And adding this up, we get, so the probability that the box that you select after switching has a prize is this, and this is obviously bigger than m/n, which is the probability that the box that you originally select has the prize, meaning it's the probability that you'll win given that you don't switch. So the probability that you'll win when you switch is bigger than the probability that you'll win if you don't switch. Thus, you should always switch.